introduce Shiqi of today's guest. Shiqi is a final year PhD student in Computer Vision Center, Autonomous University of Barcelona. He is supervised by Dr. Just. His research during his PhD mainly focused on model adaptation and domain and category shift, including source-free, continual, open-set domain adaptation. He received a master's degree in Hangzhou University of Science and Technology and once worked in Kyoto University as a research associate. You can check his personal page for more details. Let's hugely welcome Shiqi to give his talk to TrustML Young Scientist Seminar. Hi, Shiqi, please get started.
Yeah, thanks for Jingfeng's introduction. Yeah, so here I just introduce myself again. So I'm Shiqi Yang, a final year PhD student from Barcelona. And the topic of today is the model adaptation on the domain and category shift. And here I split the content into three parts. So the first part is the model adaptation without source data. So TP is the domain adaptation with source data. And the second part is the model adaptation without forgetting. And the final part will be the model adaptation on the both the domain and category shift. And then maybe next, just start with the normal domain adaptation settings. So in the setting of the normal domain adaptation, here we assume we have access to two domains. The first is the label source domains, and the second is the unlabeled target domains. So there usually exists a so-called domain shift or distribution shift between two domains. So one example is shown in these figures. The source domains may contain only the synthetic samples, the image, and the target domains will contain the image in the real-world scenarios. So the final goal of domain adaptation is trying to learn a good model, which can perform well on the unlabeled target domains. So in the typical domain adaptation, we will train the model on the both labeled source data and the unlabeled target data. Here is an illustration of the normal domain adaptation settings. So like mentioned before, we will train the model on the both source data with labels and unlabeled target data. And during the evaluation time, we only care about the performance on the unlabeled target data. So until now, we can group the domain adaptation methods so into the 6 directions. And and this image is from the tutorial in CVPRs. And actually, most of works they are based on adversary trainings or discrepancies. And maybe you will find out there is one obvious problem in the normal domain adaptation settings. That is the source data. They are always needed and necessary for the adaptations. But maybe in the real world scenarios, in the real world applications, always access to source data may not be feasible. So for example, if the large source data they are just in the cloud server side, and then you will just dispatch your pre-trained model just into the user side, maybe some mobile phones. And then for the mobile phones, typically they don't have the large memories to store all this label source data, and also in some privacy concern situations, the access to source data may also may be infeasible. So so TP here we just address we first pre-train the model. When we get pre-trained models, and then on the user side, and the adaptation can just achieved by only use the unlabeled target data. So basically, this is proposed as a source-free domain adaptations in the recent years. So at the beginning, we just pre-train the model on the labeled source data, and then we just do the adaptation with only the unlabeled target data. And finally, we will test the model on the unlabeled target data. And and through this way, during the whole adaptation process, we don't need access to the labeled source data anymore. So here I also want to point out there's a lot of related tasks. They call it a test time adaptation. So basically it's just a source-free adaptation, but the adaptation is conducted in online manners. So which means every samples in the target data, you just see it once. So so for the view of the experiment settings, there's only one apple trainings, not like many apples in the normal adaptation. And here I also will introduce several related works in the source-free domain adaptation or the model adaptations. So the first paper is the short papers. So after get the source-free tree models, they propose to just fix the classifier head and only update the backbone, which means the feature extractors. And here the objective is only contains entropy minimization, and there's also a diversity loss. And they also try. They also resort to a pseudo label for to improve the performance further. So here the entropy loss is just the margin entropies. It will make your make the prediction of your model more confident. And the second one is the diversity loss. So here you just try to avoid degeneration solutions. It try to encourage all it try to encourage the what categories will show up in your predictions. And and actually the entropy minimization and process diversity loss is just the mutual information maximizations. So this is widely used in the unsupervised clusterings. And the second related work is the HCLs in the last year's Euryx. So this paper is based on the contrast learnings. So we can split the pipeline into two paths. So the first path is they were doing the they call it a historical contrastive instance discrimination. So it's so here the objective is just inference is, but the novelty here is they use the features from the old feature structure and the current ones. So in this way, they are doing this historical. So basically, here is also aimed to try to encourage the consistency between the features from the multiple feature structures in the old or the current ones. And then they were also using the prediction from the old classifier and the current classifiers to generate pseudo labels, which will be used for cross entropy loss. And that's this paper how to do the adaptations. So basically, you can see these two papers. You can just regard these two papers as as unsupervised clusterings. So all these two papers are doing the clusterings to address source-free domain adaptations. And here, before propose our methods, we just we first have an observation about the source models. So if we got the source models and we directly utilize the target features from the source models, and we can see actually the target feature will already form some semantic clusters. So basically it shows the target feature from the source model is actually a good start for the unsupervised clusterings. So following this night, we just propose a new method from the view of totally clusterings. So as I discussed before, we already know the source feature, the target feature from the source model already form some semantic clusters. So here we just propose for each unlabeled target features, we encourage all their nearest neighbors, which means the similar features have similar predictions, and all other features they have the different predictions. So in the paper, we call this process as attracting and dispersing. And to achieve it, we define define two feature sets. The first is the CI. Oh, for each feature, we define two feature sets. The first set is CI, which means the closed set. It will only contain several nearest neighbor features of the feature i's. The second set is the background set. So in principle, the background set should contain all some dissimilar features, but here we try to simplify the trainings. So the background set will only contain all other features in the current mini batch. And and here the PI denotes the prediction of the features, which means the output of your classifiers. And then we will use the likelihood to measure the prediction similarity. for different feature sets, for either for PCI and also PBIs. So it will just measure the prediction of the corresponding feature sets. And then we will just minimize the negative log likelihood to cluster features. So minimize this objective will just attracting features in the feature space to have similar to have the similar prediction and dispersing all other dissimilar ones. And one thing I want to mention is that optimizing this objective, we can achieve the feature clustering and also the cluster assignment at the same time. And but you may already figure it out. Directly optimizing this objective is somehow infeasible because in the likelihood functions in the denominators, we need to access all the target date. So it's infeasible in the mini batch trainings. So that we will just resort to get upper bounds of the range of this orange loss functions. So actually, the final output, the final upper bound is quite simple. It only contains two dot product terms, and this lambda in the in the training upper bound, this lambda is just a small numbers, but in the experiments we just found this lambda the performance will be better if this lambda is a decay factor from a large value to small factors. Yeah, I will introduce how to tune these hyperparameters unsupervised later. And so have a close look at the final objectives. So the first dot protect, it will contain the features from the closed sets. So basically, it will encourage the features have similar prediction as your closed set. And the second one is just contain the features, contain all other features in the mini batch. So one understanding about this, maybe you can just call the first dot product as a discriminabilities, because actually it's doing some similar thing as entropy minimizations. You will have the confident prediction as just as your few nearest neighbors. And the second one actually is kind of diversity loss. So it will encourage the features in the current mini batch. Each one have a different predictions. And here maybe also some signify the reason in some degree that why we need these lambdas, because this diversity organization, they should be smaller if the features are already well clusters. So actually, through the view of this discriminability and diversities, actually we can relate several other methods in domain adaptation or clusterings. So I draw a table about this. In the tables, we just decompose the original objective for those methods into two parts. The first part account for the discriminability, and the second part account for diversities. So the first type of method is the mutual information maximization, which can be used for source-free domain adaptation and also unsupervised clusterings. So the margin entropy here is the condition entropy here is just for distribubility, and the margin entropy here is for diversities. And the second type of work is the BNM papers, is the batch nuclear norm maximizations, and it's also a paper for domain adaptations and source-free domain adaptations. So in these papers, they maximize the F norm of the prediction metrics, try to achieve the distribubility, and which is just play the same role as entropy minimizations. And in the meantime, they will also try to maximize the rank of the prediction metrics. So which means that your prediction in the current mini batch, they should contain more categories. So that's achieve the diversities. And the third type of paper is our two previous papers. It's just based on the neighborhood clusterings for source-free domain adaptations. So in these papers, actually, we are the first term is just use the few nearest neighbors, maybe by some kind of ways to do the neighborhood clusterings. And the diversity here, actually the KL divergence is just identical to the margin entropies. And also we can just look at all these methods from the view of contract learnings. So for example, here I just take the influences. So actually, one paper in the recent years, they just say the influence you can also decompose the original objective into two parts. The first part will only contain the feature itself and its its positive samples, and for the second terms, it will only contain the negative samples. So they mentioned for the second terms, actually this also kind of to put all the features just uniform in the feature space. So basically, it's also doing something as similar as diversities. And the last is our current papers with just two dot products. So basically, you can say all these methods actually achieve these two terms, but by the different ways. And then also here I show some quantitative results. Here the benchmark is with us. Actually, it's already showed it before. So the source date is only the synthetic date, and the target date will be samples in the real world scenarios. And here I show the results. The result here contain the normal domain adaptation methods, so which demand source data during the whole adaptation process, and also the several source-free domain adaptation methods. So one interesting thing is that most source-free domain adaptation methods actually they already outperform the normal domain adaptation methods. And then I show how to tune this hyperparameter lambda hairs. So like I mentioned before, the lambda hair actually we deploy the lambda as a decay values. So it will decay from the 1 to a small numbers. So here we adopt the SND, the soft neighborhood the densities is SSV papers to tune these hyperparameters. So in the SND papers, after you finish the trainings, you will take the prediction of the models, and you will compute the similarity about the whole prediction matrix, and then you do some scaling, and then you finally you compute the entrophies. So in these papers, they claim the high SND scores will signify the labels of a feature will be concentrated into very small points. So in other words, high SND scores, which means the features are well clusters. And the experiment results just are in accordance of these papers. So we just find the decay factor with the high SND scores, it will indeed have a high performance. So basically, I think this SND scores maybe also deploy to the hyperparameters in other domain application or source domain papers. Because now in the community, how to tune hyperparameter on SUAS is still remain unsolved problem. And then so we will already address the domain application without the source date. So what's next? So here we just imagine application scenarios. So we first pre-train the model on the large amount of source data on the cloud server side, and then we dispatch the pre-trained model to the user side, and then the user side we are doing the adaptation, whether the adaptation or the test time adaptation. Only on the unlabeled data from the user side, we get new models. So if this happens, we just evaluate this new model after adaptation to the original source data. So of course it will have bad performance. Because here will be the catastrophic forgettings. So the model after adaptation will lose some information on the neighbor source data. And this is typically investigated in the continued learning communities. And the reason why sometimes we need to evaluate the model on the old task on the old source domains is sometimes because sometimes it's ideas, not just retrain the models, but the model after all the trainings can have good performance on all the domains and the task. And so here, if after source adaptations, after source free adaptations, if the model will be tested on both the unlabeled target domains and also the source domains, we call this setting, we call generalized source free domain adaptations. And here is the experimental settings. So after adaptations, the model is expected to have perform well on both the target domains and also the old neighbor on the old source domains. And so how to address this model adaptation without forgetting task? So here, one simple and intuitive solution is we just deposit some certain feature dimension for the specific domains, and this specific domains may be for the old domains or even maybe for some future domains. So which means some dimension of the features, they are just domain specific. So maybe for source domains, you will only use several certain dimensions, and for the target domains, you are using other dimensions, but this dimension can be overlapped among different domains. And actually, this inspiration is just drawn from some people in the continued learning communities. And then I just illustrate how to do this. How to achieve this. So we call this method sparse domain attentions, because we use the sparse attention vectors to regularize the whole training process. So here we just first when we train the model on the source domains, we will use a source attention. So it will be just a binary vectors. So it will be multiplied to the output of your feature vectors, and and here the output of feature vector is just the vectors. It's just and this binary attention mask will just multiply to these vectors. So before the classify, and G here is the classifies, and this is a similarity. This is also for the target attention tasks. And here I show a visualization about this source attention mask and also target attention mask. So you can see these two attentions, they are overlapped, but also some attention masks may have its specific dimensions. So which means some dimension of the features they are shared by the different domains, but some are just domain specific. And then after source training, then we start doing the adaptation without source state. So for the adaptation process on the target, here we just use the multiply the target domain attention into the output of the feature vectors. And but the different things is happens in the background during the background. So during the backgrounds, when you do the updates by the gradients, we will multiply 1 minus AS to the gradient flowing to the feature vector and also the classifies. And AS here is the is a domain attention for the source domains. And here the motivation is that we what the information which may what the information or the these dimensions which may just change the source domains, they should be avoided, because now we just doing the target adaptation. Here we just care about the target performance. So everything related to the source domains, they should be unchanged. So here is why we use this 1 minus AS to regularize the gradients to update the model. And here I want to point out this: when you do the adaptation on the target domains, you can just use the label code classes or other source-free adaptation methods. So basically here the anti-forgetting is just universal for every method in the source-free adaptations. And here we draw the training process of the one task. Here we can say the source performance during the adaptation process. So it will just decrease a bit and then kind of keep stable. And the target performance will of course just improves. And here the application studies also shows this simple domain attentions, they can just avoid forgetting quite efficiently. And here I also draw some TSE visualization on the features. And the figure in the left is the feature before the adaptations, and the blue point is the source features, and the red point is the target features. So as you can see before the adaptations, because now we don't have, we only train the model on the source domains. So basically all the blue points, which means the source features, they are where clusters, but that will be not the case for the target features. So you can see for some target features, they just is totally a mess. But after adaptations, so first, because here the adaptation is already finished. So the target features, which means the red points, they should get clear, they should form clear clusters. And here, because we do some anti-forgetting things, so here the source features, which means the red point, the blue points, they should also keeping the good cluster shape, and this is just happens in these utilizations. And then actually, actually here we can also extend this message into the continuous source free domain annotations. So here we just, here we will adapt the source pre-train model to a sequence of unlabeled target date. So after each adaptation to a new target domains, the model they should keep the performance on all the old domains, which means the older target domains and also the source domains. And of course, as well as the current domains. And this is a continuous source free domain annotations. Actually, this this task is not well investigated. We are studying the community yet. And here are some experimental results. So the first domain is the source domains. We will first train the model on the source domains, with a label date, and then we will do the sequential, the continual adaptation. We will first adapt the model to the AR and also PR and finally RWs. And the result shows after each adaptation to the new domains, the model could keep the good performance on the older target domains and also the source domains. And and here I also want to point out there's a lot of related situation, related settings. They call it continuous test time adaptations. So basically, it's a kind of related to new task in just some people in the in these years address these new settings. So basically, it's just same as a continuous source free domain adaptations, but it's still doing things in online. You will only train on each samples once, and then you will don't see these tables. This date. And so until now, either the domain adaptation or the source free domain adaptations, we only assume the domain shift with distribution shift, but the label space from the two domains, they are identical. And here I just some here I put some related settings. So related to whether this setting have the domain shift or even the category shifts. So the first setting is the open set recognitions. So in this setting, you only have the category shifts. So which means your training set and the test set, they may have a different label space, but there will be low domain shift. And then will be the domain generalizations. So actually for domain generalization, there are also, you can split a domain generalization into two subsections. So the first, the normal domain generalization, you only have the domain shift, but without the category shift between the different domains. But a new setting will be the open domain generalizations. So here, your several target domains, first it will have domain shift, and then they also have the target domains may also contain some normal categories which is not seen in the source domains. And this is similar. This is similar as the several domain adaptation settings. They call open set or universals. The universal here is just the open partials. So which means some categories, they may be shared by the source and target domains, but also each domains have its domain private categories. And then we just take a step further. So can we just address the domain and also the category shift during the source free adaptation process? And then maybe we just check the experimental setting of this open set recognition or other settings. And first for the open set recognitions, so most papers they only will they will only train the model on one label date. And here the label date only have the in distribution date. Here the distribution is just a symmetric distribution. And during the evaluations, they will directly evaluate a model, which is already trained on this label date on a large group of unlabeled data. And here the unlabeled data may contain the categories which is already see in the training set, but also it will contain some OOD samples. Here the OOD just means the lower categories. And the another related set is the like mentioned that tables is the open set single domain generalizations. So here compared to the normal domain generalizations, here we only have one single source domain. And so here we just train the model on the source domains, and then we will directly evaluate the model on the unlabeled target domains. And in the unlabeled target domains, so first it will have the domain shift, and then also maybe some unseen novel categories may show up. So here just so here things just get more challenges because you need to just address the domain shift, and also you need to distinguish which sample is from novel categories. And the last setting is it will be the universal or open partial domain applications. And here I also put this setting the source free settings. So we are pre-train the model on the source date, and then we will doing the adaptation on the unlabeled target date, and then we will evaluate the model on this unlabeled target date. So the reason why we call it universal or open partial is that in the target domains, so some categories which is already seen in the source domains may be just missing, so we will not see it anymore. And also some novel categories may show up. So basically here you need to detect whether this sample is from the old is from the C categories and also from the U categories, but because some categories is missing, so basically there are some bias and imbalance problems. And here we have low prior information about which categories are shared or private. And then in the next I will mainly introduce one related work in the source-free universal or open partial domain adaptations. So actually these figures there are two papers in the CVPR 2020s. So the key parts of these two papers to address the category shift is that they try to synthesize some novel categories, and this process is before the adaptation, which means they will do it during the source pre-train process, because they claim that if when you do the source pre-trains and you just add this synthetic on those samples into the trainings, so the descending boundaries will be compact. So which means there are some feature space will be left out for the future unsafe categories. So that will be that will be good for the adaptation process. And actually this kind of process is also adopted by several methods in the open set recognitions. So here either for the normal open set recognition or the open partial or universal domain applications. So the purpose of this open set path is just trying to get open class detectors, which is able to reject all the unknown samples. But like showed before, and most works in this open set recognition and also open set domain adaptation, they try to synthesize unknown samples. So this may be heavy and memory consumers. So here, what if we don't use any unknown samples? So without actual samples and also without generating these unknown samples, we still want to get a compact descending boundaries and also leave out some space, either the feature space or some or in the output space for the unknown samples. So here, so try to to achieve it, we just assume that the second code set here the closed set is for the C categories. So the second closed set will be any. It may be similar to the unC categories in the futures. So here we just implement this assumption just change a bit to the classifiers. So for the normal classifier, you will only so typically in these settings you only know the number of the source categories. So the dimension of the classifier will just be the same as the source numbers. And here we just insert one actual dimension to the classifiers. This dimension will be corresponding to the unknown categories or the normal categories. And then follow the assumptions. So first we will train the whole networks is just a pipeline. In this stage we just train the model on the source data, and the source data only contains C categories. We will train this pipeline with two signals. The first signal is the normal signals. We will use the ground truth label to train the signals, and the second signals. And as for the second signals, here we want to assign the second maximal nodes to the classifiers. So to achieve it, we first remove the dimension corresponding to the ground truth categories. So now the remaining dimension, they are either belonging to the non-ground truth categories or the unknown categories. So here we want to assign for this remaining dimension, we just assign the maximum value to the unknown samples, to the unknown dimensions. So training with the two signals. So basically, we just ensure two things. First, for the samples in the source state, it will have the correct prediction to its ground truth labels. But second, for one sample in the source state, which means the C categories, the second maximum nodes will be the unknown samples. So which means it will have high possibility to belonging to unknown samples than belonging to the wrong categories. And so this is what we propose. We call it one because we just add one actual dimension to the classifiers. And and actually there's one similar papers in the open set recognitions. They were already doing the similar things in the this paper is in the CVPR 2021. And here I drew I put the advantage here. So here we have two advantages. First, here we don't need access to the actual novel categories, or we don't need to generate this auto distribution data. And also the second advantage here is the whole training process is quite simple. It just simply enforce the unknown class have the second maximal nodes. And then we will show that with this simple pipelines, we can achieve quite good performance on either the open set recognition and also this. First I show some results on the open set recognitions. So here, so maybe I just show the visualization here. So here, so here we first train the model on the 15 node categories. And this one now, the one is actual dimensions, and the figure in the left is a TS engine visualizations. The dot here is the features, and the cross here actually is the weight of the classifiers. Here we regard the weight of classifier as prototypes. So here you can see after training on the source state. So what the samples in the current domains, because they are C categories, so they will be just gathered around the corresponding source prototype. But for this actual dimension, the actual prototype, because it denotes unknown categories, and here is no samples, so it will just alone in the colors. And then we add 10 unknown classes into the evaluations, and we also do the visualizations. And here we can see this 10 unknown classes. So typically most of these unknown samples will not gather around some specific node prototypes. So it will just in some space far away from all these node samples. And also here the unknown prototype will not be known anymore. So all these unknown categories will just somehow it will gather around in these actual prototypes. And here I also put a demo here. It's a demo about how when you train the okay. Yeah. So it's starting. So the lab is just train the model on the with a normal signals, the normal signals, and also only with the samples in the C categories. And the right is just a train with the two signals, like we proposed. And here we have 3 node samples, and the purple is the unknown samples. Maybe start it again. Yeah, so you can see if, when you train with 2 signals, so basically here the feature space will always leave out some paths for the unknown categories. So that's it. So basically it shows that this training pipelines without any actual unknown samples, it can quite efficiently distinguish which part is the unknown samples. And then so we already addressed the open set recognitions. So then we just want to also consider the domain shift, but here is the open set domain generalizations. So here we just here for the target data we just evaluate on it. We don't do any adaptation on it. And here we I just put some quantitative results here. So basically here I compare with our methods. The wiring S it just train on the label source date with the C categories. We compare with several methods which is tailored for the open set single domain generalizations. So so keep in mind here what other methods here it will have actual module for domain generalization. So they will have a typically OS stars the high OS star scores. The OS star here denotes the accuracy for the C categories. And here we just want to emphasize that even under this categories, even under the domain shifts, our methods can efficiently detect the open classes compared to all these other methods. Because we have the higher UNK scores. And here the result shows this simple pipelines just can detect the open class even under the domain shift. So then the next step will be doing the adaptation. So here is the source free universal or the open partial domain adaptations. So at the beginning, which is same as the normal source free adaptation, we just pre-train the model on the source, and the source only contain the C categories. And then we will doing the adaptation on the target date. And so please note that the target date here is will contain the category which is not seen in the source date. Also, some source C category will be missing. And finally, we will after adaptation on the target date, we will just evaluate the model on this target date. So we already know this pipelines after training on the source, it's already quite good at to detect open class even on the domain shift. So one natural idea how to do the adaptation is just to use the entropy minimization on the target date. But here will be one program for directly deploying the entropy minimization. So there will be imbalance problem. So in this I think in all these benchmarks. So in some benchmarks, the target data may have much more samples than the the on-C categories in the target data may have much more samples than the C categories. So if we are directly doing the entropy minimization, so this imbalance issue, so basically it will crash the models. And this is a similar way if we have this is a similar situation if the the samples from the C categories have more is more huge than the on the novels. So I just show one I just show one result on the this is the benchmark. I think it's on the on the office homes. So the first row is source models. So source models, it will have a high UNK score thanks for the wiring pipelines. So here, if we just do the entry minimizations, so you can see after the adaptations, the UNK score will be quite higher, but for the OS star score is the score for the low accuracy will be quite low. So which means the most samples from the C categories will be misclassified as unlow categories. So we reported that this issue is due to this imbalance problems. So try to address this imbalance problems. We just do a really simple modification to the entry minimization. We just introduce a weight, and here the weight is not set by some threshold manually. We're just using the prediction of of the current models as a weight. So here like the entry minimization. Before I split entry minimization into two parts. The first part is for the samples, which is predicted as C categories, and the second part is the samples which is predicted as unknown categories. And because the training process is is in the mode of mini batch. So here the entry minimization is also in the mini batch. So here the weights for the first part will be the number of the predicted node samples in the mini batch, and that will be the similar for the second one. Second one is the number of predicted unknown samples in the mini batch. So with this little modification, actually, the entry minimization can works well compared to the original entry minimizations. So after adaptations, the known accuracy and the unknown accuracy will all improve. And here actually the entry minimization is just a baseline for the domain adaptations. So actually we can also insert some other source free domain adaptations into this into the entry minimizations. So here we choose to insert our previous papers, the AED papers I just present in the second part into this entry minimizations. So basically and here I show some experimental results. Here is for the open source free open partial domain adaptations. So note some category will be shared and some category will be domain specific. And here is here the OS is the average accuracy across all the categories, and the H here is a harmonic mean between OS star and UNKs. The OS star is accuracy on the C categories, and UNK is for the open class. So here for Office 31 and the results for Office 31, so I showed performance in the metric for OS and H, and for results I showed performance on only in the metric of H, just like related works. So first, one interesting stat is on some data sets, maybe the Office 31, the source model even have quite decent performance compared to the methods already finished adaptations. And then after adaptations, we can get quite higher performance. And when augmented with other source-free the domain adaptation methods, the performance can get a huge improvements. And I also show results on the Office Home. Office Home have more. Here actually you have in this I think compared to the results here, the unknown sample here we have more unknown categories compared to the C categories. And here like the related works, I only show the H scores here. So basically here the conclusion is just similar as the two benchmarks. So first for the one ring S is just a source model of the trainings. Actually, it can get quite relative high performance compared to the methods already finished adaptations. And then we do the adaptation with only the weighted entry minimization. We can get decent performance. And after augmented with the other source-free adaptation methods, we can still get huge improvements. Yeah, so here so that's the content here. I put a conclusion here. So first, we show that the unsupervised clustering is just an efficient way to address a model adaptation. And then we show a simple attention-based regularization can achieve the continued model adaptations. And finally, we show that just inserting one actual dimension to the class size, and we can address a domain and category shift and during the adaptation at the same time. Okay, so that's all, and thanks for your attention. And actually, you can find all these contents in my homepage. And of course, if you have any questions, I'm happy to answer.
Hi, Shiqi. Great to talk. I just have a general questions in terms of work. So when I heard about the domain adaptation out of distribution, I always have a question is how to measure the differences. Because we know that if the domain is very, very different from the source domain, I think the adaptation will be very, very challenging. And also there existing some adversarial data looks very similar, but it's very different in machine learning perspective. So how do you comment on this?
So it's true that for the term domain adaptation, of course, the source domain and the different domain, they should share some similarities. So for the first question, if you mentioned this difference, if the difference is quite huge, so I guess so I guess there will be no adaptation anymore. So maybe it's just like you just train your model on the on the source, and then you fine tune the model on the target.
Yes, right. So right. Please.
So actually you see all these methods. Most of these methods they can address source-free domain adaptations. And note, and actually, if we are doing things from a view of distribution and diversity, actually these things they are just doing the unsupervised clusterings. So I guess for this source-free domain adaptation methods, so maybe even this shift is quite huge. Maybe this method can still works. So here, so in that case, they will be just the clusterings. So it's not called adaptations. So here maybe here the domain shift is really huge. Maybe even the category, they are total difference. Maybe here we can just remove the classify, and we just doing the feature clusterings. I guess most of its works can also works.
Yes, I see. So the reason I'm asking this because in reality we want to use the domain adaptation. We don't know in which scenario we can use it in proper way because we don't know how to measure the differences between the target domain and the source domain. And for example, if the difference is good, is small, then we probably can use some domain adaptation techniques. If it's too large, like you said, we maybe just model the target domain from scratch. So that's why I'm thinking how to measure the differences to check whether we can use it or not.
The different domains share the same category or not. So if the different domain have a different domain or different dates, they have the same label. So I think it will be no problem. The source domain adaptations.
I think from your side is maybe some voice, maybe some problem. I cannot hear you clearly.
So if so now it's fine. So if the label space is the same, so I guess they all this message will still works because then the adaptation will just become a clustering problem because the label because label space is the same. But if the label space is not the same, then it may be hard.
I see. I got it. Yeah, right. I see. Okay, thank you. I think there's another question in your chat box. Can you read it and answer it? Yeah.
Oh, the augmented weight signals. Oh, yeah. That, so you mean the here? So actually the here is just the sort weight documentation I introduced in the second part. Yeah, so it's so here is just these two dot products in our previous papers. So actually you can just replace it with all the other things in this table. So is that clear?
Yeah, maybe I think so. Yeah.
Yeah.
All right. If there's further questions you want to ask to Shiqi, you can definitely email him for more questions. Thanks, Shiqi, for your great talk today. Thank you. Okay, good. Hi, everybody. Wu Han is a PhD student in computer science at Eiffel, advised by Amir. He got his bachelor and master degrees in electronical engineering at METU, Turkey, in 2017 and 2019, respectively. His research focused on building robust and general visual perception systems that can operate in real world. Let's welcome Wu Han to give his talk on 3D common corruption and data augmentation. Hi, please get started.
Thanks a lot for the introduction. Can you see my slides?
Yes, and also can hear you clearly.
Okay, awesome. Okay, hello everyone. My name is Oğuzhan. I am a PhD student at EPFL. Today I will present our work appeared at CVPR 22. It's 3D common corruptions and data augmentation. It is joint work with Teresa, Andre, and Amir. So let's get started. Yeah, as shown many times before, also in the previous presentation too, computer vision models are brittle in the real world due to distribution shifts from training data. Let's see this on an example. So this is an input image from an indoor scene, and this is the corresponding ground truth label for surface normals estimation task. So for this task, you don't really need to know the details, but basically each pixel here is showing the orientation of that pixel in 3D space. For example, if it is purple, like in the floor, it means it's pointing upwards. If it is green, like in the ceiling, it's pointing downwards, and so on. And this is an important dance prediction task for several applications, like for example, in robotics. And I will mainly use this task for illustrating the ideas throughout this presentation, but then I will also show results for other tasks too, like depth estimation, semantic segmentation, image classification, and so on. But for now, let's stick to surface normals. Okay, now, as you would expect, we can train a neural network to predict surface normals given the clean image. And by clean image here, I mean this test image is similar to the data that the model is trained with, and there are no particular corruptions or distribution shifts involved here. And yeah, when you input this image to the model, as you see, the predicted surface normals are reasonable and they are like somewhat similar to the ground truth normals. So then we can assume this model is working well. Okay, now let's change things a bit. And for example, let's change the depth of field of the same image. And what do I mean by that? Basically, you can just take your DSLR camera and you can just play with its focus. And here, for example, we focus on the chairs at the right side while the rest of the scene gets blurry. And now, instead of the clean image, let's feed this image to the model. And this is the predictions from the same model. The only difference between the two is just the change in the blur, like the change in depth of field. However, also note this, please. Like for us humans, the scene geometry and surface normals is still perfectly recoverable. Like for example, when we look at the floor, we can still understand its normals, like where the orientation of each pixel in the scene. So for us, there's not a really big difference between these two images. But for a model, there's a huge difference actually, and you can see it from the predictions that are collapsed terribly. And this is just another example where instead of changing the focus, we added some camera motion blur to the image, which can be very also plausible, because when you take a photo in real world, you may have some handshake, and because of that, you may have some motion blur in the input. And when you feed this input to the model, again, your predictions are getting much worse than what was the clean predictions. And obviously, this is a big problem. And let's see this on a video now. This time, I hope this video is playing well on your side. But here, what I'm doing is basically, I'm just changing the focus of the input and increasing the blur level. So as you can see it from the shift intensity bar at the bottom. So as you progressively increase more blur and more, you see the predictions gets worse and worse. And obviously, none of this is about adversarial attacks. Like this blur wasn't generated adversarially. It is just a common blur that you can see in real world. So this is nothing about adversarial attacks. And then this is actually a critical problem that needs to be solved before deploying these models in real world, right? And this is the main motivation behind our work that I will present now. So previously, as many of you may already know, a common corruptions benchmark has been proposed to evaluate models against several distribution shifts. And these shifts are obtained by applying different corruptions over the image, such as Gaussian noise, defocus blur, snow, frost, fog, and so on. And basically, they take some real images and then apply these corruptions on these images to generate some distribution shifts. And then several other works extend this benchmark. So this was originally proposed for ImageNet classification and CFAR classification, but then other works extend this to other tasks like object detection or semantic segmentation. This benchmark provides, it's a useful tool to understand model vulnerabilities. However, there's a problem that we are pointing in our paper, which is this. So this common corruptions only considers simplistic 2D modifications over the images. And I will explain more on that soon. In other words, they are not taking scene 3D into account. Hence, this results in corruptions that could be unrealistic. And this is problematic because if we evaluate models with corruptions that don't reflect real world well, then we may reach at wrong conclusions about robustness of these models. And obviously, like when they are faced with real world corruptions, we will see a discrepancy between their performance on this benchmark and real world. And because of this, in this work, we consider a different approach. And while generating the corruptions, we incorporated the 3D information and real world scene properties. And as I will show next, this results in more realistic corruptions that could be used for different purposes, not only for benchmarking. So basically, the main outcome of our paper is a diverse set of realistic corruptions, ranging from motion blur to lighting and occlusion changes. For example, let's look at motion blur first. So here, the 3D motion blur at the top obeys parallax, motion parallax. You can see it from the yellow circle, like ellipse region, where the chair at the end of the corridor having less blur than the walls nearby, obeying the parallax. And this is in contrast to 2D motion blur at the bottom, which has been applied uniformly everywhere. And this is not the motion blur you would see when you have a camera motion in real world. Similarly, here we are seeing 3D defocus blur. And basically here we can change scene depth of field and change the focus region. For example, here we are focusing on the car while the rest of the scene is getting blurrier and blurrier. However, if you look at the 2D defocus blur case, it is just applying the same blur uniformly everywhere. In other words, if you go with 2D defocus blur, you won't play with the depth of field effect, which can be commonly faced in the real world. You would only experiment with uniform blur. Likewise, in the 3D case, here we are showing illumination changes. So in the 3D case, illumination changes take the scene geometry into account and generate shadows as you see above, and it will be a non-uniform lighting throughout the scene. And this is again in contrast to 2D lighting changes, where each pixel is, the brightness of each pixel is just increased linearly or decreased linearly without taking the scene geometry into account. And likewise, this is another example with fog. So basically in the 3D case, fog gets denser as you get further away from the camera, which is what you would expect. Like see this end of the, like the tower of the church is getting less visible and visible with higher fog intensity. And if you contrast this to the 2D fog case, you don't see a change in the visibility of the scene. So then it's obviously it's not a very realistic fog. And also in the 3D case, occlusions occur naturally. For example, here we are occluding the fridge shown in blue by the plant by changing the camera position smoothly. And this is possible in our case by placing the camera in the scene in a particular way so that one object occludes the desired object by a desired ratio. So here we can just control for we can just condition on one object, like for example, fridge, and we can set the camera motion in a way that the plant will occlude this in a particular way and in a particular occlusion ratio. And we can control that. And note that this is quite different than the commonly used 2D occlusion at the bottom, like in cutout, for example, that drops random patches, which is obviously not very natural. So next to the more geometric corruptions that are shown on the left, this is also a new class of corruptions that we introduced in this paper, which we call the semantic corruptions, because here the corruption is conditioned on the semantics, scene semantics. So in total, we created 20 different corruptions, which we named as 3D common corruptions, or 3DCC in short. And they address different aspects of real world, such as depth of field changes, like focusing on the far scene and or the near focusing on the rear region of the scene, and or semantic changes like occluding the scene or changing the scale of the objects, weather like fog, lighting changes like adding shadows, like generating increasing shadows, having multiple illumination or adding flash to the scene. View changes like changes in the camera pitch, roll, field of view, or also having some jitter in the view. Motion blur due to camera, like for example, XY plane motion or Z direction motion and resulting blurs. Video-based artifacts like bit error or some compression artifacts. And finally, some noises. These are not 3D. But like the dash line, the right of dash line is not 3D, but the left ones are 3D informed. And so overall, we obtain a diverse set of distribution shifts. Okay, cool. So before delving deeper into the usefulness of these corruptions for different purposes, let's take a quick look at how to create them first. So most of the corruptions require an RGB image and its single wave depth, while some other requires a 3D mesh. And this figure summarizes which inputs are needed for a corruption type. So based on its category, whether it's view changes, semantics, or like noise, you can generate the corruptions from the RGB image and its 3D information using our repository. And to generate each of them, we leverage the techniques from 3D synthesis and image formation models, and we use common tools like Blender and PyTorch. So you can generate them easily, and you can integrate them into your own pipelines. As an example, let's take a look at how to generate depth of field effect, for example, in an efficient way. Of course, there are many other ways to do this effect, but here we just pick one for efficiency. Here we first split the scene into multiple layers, as you see here, by discretizing the scene depth. And then we choose a region to be kept in focus. Here we are picking the closest, the region closest to the camera to be kept in focus and rest of it to be out of focus. And then we then compute the corresponding blur levels for each of these layers according to their distance from the focus region using a pinhole camera model. Then we obtain the final refocused image by compositing these blurred image layers. And as you see at the end, this part is in focus and the rest of the scene is out of focus. So this is just an efficient way to generate depth of field effect, and you can play with its focus region, its blur level, and so on. And in the paper, we also explain how to generate all the other corruptions too. And yeah, we also provided the implementations for each of these corruptions. So, okay, then now we can move with the significance of these corruptions. Like, okay, we are saying we are generating some realistic corruptions, but what are the purposes actually? So in this work, we study two different use cases of these corruptions. The first one is to create a benchmark to test model robustness against distribution shifts. Now, I will show that this 3D CC or 3D common corruption is a challenging benchmark for models. And further, it exposes vulnerabilities that are not captured by the 2D corruptions, like in common corruptions. And for the benchmark evaluations, let me give some preliminary information first. So we trained the models on Taskonomy and Omnidata datasets. Taskonomy includes 4 million real images from indoor scenes, and Omnidata is even larger with 14 million images from 2000 scan sprints. So Taskonomy was only indoor, but Omnidata also has outdoor scenes. Both of these datasets are from our lab, and they come with labels for several tasks. So I highly recommend taking a look at them if you are working on like multitask learning, or if you are generally interested in like 3D and so on. Here I'm just showing an example for Omnidata. It basically takes this pipeline, Omnidata pipeline takes as an input a 3D scan. And this can come in many different forms. It can be a textured mesh, it can be a point cloud or something else. And from this scan, it can generate a data set with several domains like segmentation, depth, normals, and so on. So here, there are like 21 different cues that you can obtain from the scan, also like including the input image. And you can also check the project page for more details. Okay, cool. Now let's look at some qualitative results first. So here, similar to the first slide of this talk, there's an input image, and we will apply 3D motion blur to it. And we will progressively increase the intensity of the blur, which you can see from the bar at the bottom. Then here you will see how the change in the predicted normals, and at the right, you will see the change in the L1 error. So let's play. As you see, model performance degrades more and more, and you can control for the amount of corruption you apply and obtain a fine-grained understanding of the robustness against this corruption in particular, for example. And similarly, this is another example for near focusing. We see that errors increase significantly and non-uniformly throughout the scene. And again, you can quantify this with 3D CC. Okay, and let's look at another case now. And this is for semantic segmentation. And here the corruption is occlusion, object occlusion. And this time, the model is a detector-on model. And the rightmost plot will show the IRU score as a function of occlusion ratio. And here blue and red shows the A model visible and occluded parts of the fridge from which can obtain the occlusion ratio. And as you see, when occlusion ratio is above 25%, performance this detector model drops severely, as you can see here. And here we are showing this for a specific object, which is fridge here, but actually you can perform this occlusion analysis for many other objects in the data set too. Okay, now let's also take a quick look at some quantitative results too. Here we benchmark several robustness mechanisms from literature, such as adversarial training, style augmentation, diverse ensembling, and deep augmentation. And we also added this baseline where we basically augment the training data with the corruptions from common corruptions. So this is why we call this like 2D common corruptions augmentations. And here we show the results for surface normals and molecular depth estimation tasks in terms of L1 error, so lower is the better. And the red lines show the L1 error of the baseline model when there's no corruption applied. So this is like you can think of this like a gold standard where the model can reach. And as you see, all the robustness mechanisms are performing quite bad against 3D common corruptions for both tasks, and they are insufficient to address the distribution shifts occurred. And you can also see the performance, the variation from the bars, which is quite large for different corruption. Like which shows the performance is varying quite high, quite large for different corruption types. And let's take an even closer look to different corruption types. And here we test 3 models trained on 2 data sets, taxonomy and omnidata, and 2 different architectures, UNet, which is a convolutional neural network, and DPT, which is a transformer-based architecture. So we also want to understand what is the effect of architecture on robustness. As you see, these models react differently to different corruptions from 3D common corruptions. And so understanding these vulnerabilities to each of these corruptions could be particularly useful depending on the application that you are interested in. And also it's important to note that here the transformer architecture DPT models are generally performing better than CNN architecture, which is like UNet architecture, which was also observed in previous work. And here in the legend, the numbers in parentheses is showing the average error across all the corruptions. And we are seeing the highest improvement in L1 error when we trained the model on the data sets with DPT architecture. And these are more quantitative results. This time, again, smooth changes in the viewpoint, like camera field of view, roll, and pitch. And again, we see the largest benefit when omnidata and DPT are combined, which is the green line here. And finally, another quantitative result for semantic segmentation this time. The previous ones were for surface normals. And this is the performance of the same detector model that I showed in the video against occlusions for different objects when it's trained with taxonomy and omnidata. And again, we are seeing omnidata model is performing generally better and it's more robust to occlusion. So as you increase occlusion ratio, both models degrade in IOU, but omnidata is degrading either slower or degrading at a much higher occlusion ratio. But still, it will also severely degrade for high occlusion ratios, like around like 75% and above that ratio. Yeah, and this was all about benchmarking. We have like more analysis and results on the paper too, but I think this should give a high level idea to you. And now I want to move on with the second use case of this 3D common corruptions. And what we showed in the paper that besides benchmarking, the second use case of these corruptions is actually using them as data augmentation during training. And here the reasoning was as follows. If these 3D corruptions are indeed similar to the ones in real world, then it's a natural question to ask whether we can robustify a model using these corruptions as data augmentation during training. So in other words, this time the investigation is usefulness as augmentation instead of benchmarking. And our answer is positive here. We show using these corruptions as augmentations resulted in significantly improved robustness compared to baselines, both qualitatively and quantitatively. And for the experiments, again, we consider surface normals models trained on taxonomy and omnidata datasets. And our model starts from Omnidata plus GPT-1 and as the augmentations, the 3D augmentations. In fact, we also have a live demo in our project page where you can try your own images and see how it performs. And it's for both normals and depth tasks. So I highly recommend taking a look at them too. And now let's look at some results. In the results that I will show on videos, all the predictions are obtained frame by frame, so there's no temporal information used. And this is an input from a sample YouTube video, and the frames exhibit distortions due to compression and other artifacts. And from this frame, you can see that like we are comparing to Taskonomy plus UNet, Taskonomy plus DPT, Omnidata plus DPT models, like these three baselines, and this is our model. And as you see, our model is notably more accurate and consistent with the scene geometry. And now let's play the video. Yeah, and it also generally produces predictions with less flickering, even though it doesn't use any temporal information. And this is another scene with large distortions due to camera motion and compression and probably other things too, like noise and so on. And again, we are seeing better predicted surface normals with our model. Yeah, and you can see this more clearly on the frame and on the blue circles. And this is another view from the same video. Overall, what we are seeing is that using these 3D augmentations notably improve robustness against real-world distribution shifts. So this was a YouTube video that we just like took from the net. We didn't add any corruptions to this. This already came with like some real-world corruptions already. And what we are seeing is, even though this model never saw any of these corruptions, the approximations we made in the 3D common corruptions actually helped to get better results on this video and many other results. So these are other results, like other queries that we collected from different sources, like these are from Oasis. This is from like After Effects, like generating some changes in the scene with using some, photorealistic synthesis technique. These are from taken with a DSLR camera, and these are from YouTube scenes. And here we are comparing against Oasis and Omnidata models, which are state-of-the-art models in surface normals estimation. And the last row is showing our predictions. Again, the predictions got more accurate and sharper in general compared to both baselines. And let's look at more qualitative results from the Oasis dataset. So for example, this example has a blur in the background, and both Taskonomy models couldn't handle it well. Like neither the Taskonomy plus UNet nor the Taskonomy plus DPT models. So Omnidata model improved upon Taskonomy ones, but when you add 3D augmentations on top of Omnidata, it did even better than that, which you can see from the background and like for example, like the details here, which are missing in the Omnidata one. And another example here, you are seeing the predictions are getting much sharper and consistent with the ground truth compared to the other predictions. And yeah, we obtain also similar results for molecular depth estimation too, like compared to MIDAS, which is another state-of-the-art depth estimation model. We are getting sometimes better or sometimes like similar performance. And like from the live demo page, which you can access from the project page, yeah, you can also just upload your own image, or you can also look at the previous uploaded ones. Like there's also an archive of previous uploaded queries, which you can scroll through and like compare the model predictions. And you can also access model weights, of course, to run it for your own purposes. Cool. So this was all about the data augmentation aspect. Finally, I want to briefly talk about the application of 3D common corruptions to standard vision datasets. So note that for all those things I discussed, one needs depth, like some sort of 3D information to generate these corruptions, right? However, we know most of the data sets that we are usually using, like ImageNet and Coco, they don't have 3D labels. So what we did was we instead used the predicted depth from the model that we trained with the augmentations, and we use it to generate the corruptions. Basically, we treat it as the pseudo ground truth, and we run the pipeline using the predicted depth coming from our molecular depth model. And yeah, when you look at the queries from ImageNet and Coco validation sets, like you can see that this indeed works. This indeed works, and this can generate like visually plausible corruptions, like changing like near focus, far focus, fog. And we also quantified that this is indeed a reasonable approximation of the corruptions. Let's also look at some changes, like by increasing the shift intensity. Like for example, here we are performing near focusing on ImageNet samples, and we are increasing the shift intensity, so the background is getting blurrier and blurrier. And like here we are focusing on the stock, for example, or this part of the church, while the rest of the the tower is getting blurry, or like similarly here, this part is in focus and the rest is out of focus. And so these were from ImageNet. And so there's no ground truth depth for these things, these images. And these are from Coco, and this time we are applying fog to them. Yeah, you can see that the fog is looking generally plausible, and it's fitting our intuition. Like it's getting less visible and visible as you go farther away from the sea. And in fact, motivated by this results, we also introduced ImageNet 3D CC benchmark, basically applying the 3D CC, 3D common corruptions to ImageNet validation set. And we picked 12 of the corruptions from the whole step to collect this benchmark. And you can see samples from this benchmark here. And in fact, this benchmark is also incorporated into robust bench and shift happens benchmarks, which are commonly used in the robustness community. So you can also directly use these benchmarks to access ImageNet 3D CC as well. And I put the links also here. Yeah, here I'm just showing an example from the robust bench repo where you can follow the instructions to download the data and use the evaluations, like sample evaluation script to obtain your results. And you can also do something similar for the shift happens benchmark as well. So to conclude, in 3D common corruptions, we show that it can work as a challenging benchmark to evaluate robustness. Also, it can be used as 3D data augmentation mechanism to improve robustness for several tasks. It is extendable to standard vision datasets like ImageNet and Coco by leveraging predicted depth. And it's also easy to generate and efficiently compute, so you can use most of the corruptions on the fly during training to, if you want to employ them as data augmentation without incurring a high cost on the training time. Okay, I think this was it. There were more details and additional like evaluations we did and analysis, but maybe this is a good time to stop and take questions. So thank you.
Thank you very much for a great talk. It's really, really remarkable and very awesome to see your great work. Deserve the oral. Yes. Yeah, I have one question. Let's be in general. So the method you developed, it will be the full coverage of the corruptions, or just you use it several corruption you think is may happen in the real world, because we can always find some corner case that may not coverage in the generation method you propose. So how do you comment this? Yeah.
Yeah, this is an excellent question. Exactly. So our aim is to not to collect all the corruptions that can happen in the real world. I think it would be impossible, and it wouldn't be very practical to do as well. But this is more about just pointing the direction that the corruption that we are working on should be closer to real world. Like this set is by no means like it's not a sufficient set, right? There are some useful corruptions probably that will reflect some of the corruptions that you will see in real world, but by no means they are covering everything. So of course, adding more and more corruptions will be definitely useful in the future work.
I see. Yeah, Salah, you can see something.
Yes, thank you very much for your presentation. It was very insightful. I already used your approach as part of robustment, and yeah, it's really effective to test models. I had a question about the overheads, the computational overhead, because in your second way, when you combine your detector, depth detector in the pipeline, I was wondering, because if you need to do it in real time as data augmentation, isn't it too expensive to run? Or what are the implications?
Yeah, if you don't have the ground truth depth, like you cannot use a data loader to just load the pre-computed depth. Of course, you also need to take another additional forward pass during training. Basically, you need to take another pass from the depth model to get the predictions, then apply the corruptions. So this will incur a bit like overhead on top of what you already need to do with augmentations. But I guess for most of the settings, one can already pre-compute the depth. Like either there can be ground truth depth like in Taskonomy or Omnidata, or you can just run the model on ImageNet or Coco to get the depth and then save it and then just run the pipeline online then. So I think, yeah, like there will be some cost by applying these corruptions on the fly. I think if you assume you already have the depth pre-computed, it should add around like 10 to 20% overhead on average. So it is definitely something, but it's not really adding like a lot of time on top of what you already need to do. So, but there is also other trade-offs, like you can also maybe pre-compute some of the corruptions. You don't need to compute everything on the fly too. So it really depends on the computational budget, I think.
I see. Hope this answers your questions. I saw another question in the chat box. Can you read it?
Yeah. So the question asks, how does the resolution of the data affect 3D CC? So, so most of the corruptions that we are applying they don't depend on the resolution. So because they are using some classical tools. Obviously, if you increase the resolution of the image, it may take more time to generate the corruptions, but the quality will not depend on the like. Obviously, if you have more high resolution, the prediction, like the quality of the corruptions will be better. But yeah, it will basically just increase the cost the computational cost of the pipeline, not the quality.
I see.
Because we are not using a neural network to generate the corruption. It's a classical approach.
See. Yeah. Okay. If there are no further questions coming up, let's. Oh yeah, there is another question. Hi, Salah.
One last question. Sorry. I was wondering in your approach. You know, there are a lot of research now in adversary attack that try to tackle non-LP attack, which means how we can analyze similarity between the generated data and the original data without using LP distance. So I was wondering, what is your take on this kind of new research? So non-LP distance when you talk about 3D corruptions, because in this case, it's even harder to define this similarity metric.
Yeah, I think, yeah, actually that's a good question. So we had a similar question in mind when we were trying to quantify the difference between the 2D corruptions and 3D corruptions. Like we are saying these two are different, but actually how much they are different at the end of the day. So for this, we made some analysis on, like we try to use different metrics, like just a pixel error, like L1 difference between the two images coming from these two different corruption types. and also some other, metrics, like instead of their difference in the image domain, their difference in the prediction domain, because we are doing some dense prediction task like normals or depth here. Or you can also, you don't need to do L1 error. You can also use some other like metrics like LPIPs or SSIM, like different kinds of things. So we also experimented with these kind of things, and you can also see them in the paper. But I don't think there is an optimal way to measure these differences. This is like these things will say different things, like in terms of the difference between the images, but I don't think none of them will be conclusive. So at the end, we will still resort to some human intervention to say like how much they look different. But from models perspective, yeah, it's a whole different scenario too. Like from a model perspective, they may look completely different.
I see. Thank you very much.
Thanks again for Uzhan's great talk. If you have a further question, you can email him to ask about it. So I think Japan right now is open its border. If you have time, please visit our center physically in the future.
Awesome. Thanks a lot.
Thank you. All right. This is the end of today's seminar. Yeah, bye-bye.